We have a sequence of 2 talks exploring a little bit the future of computing. Yeah, and the first of these 2 talks is by Dr. Gabriel FONSECA GUERRA from Intel, and you see the title is about brain-inspired and energy-efficient solution to hard optimization problem. Gabriel, thank you very much. You're most welcome to start with your presentation. Thank you.
Thank you very much. Just audio check. Is the audio working?
Can see your slides and we can hear you clearly. Thank you.
Okay, that's perfect. So thank you very much. It's really an honor to be in an ICTP event after all you have done for physics. So that's I'm really happy for the invitation. And what I want to talk about is, yes, as I said, like a technology that we have been developing in Intel for probably 6 years or so, that is taking inspiration for how the brain computes. And we have been exploring many applications, and the application that I want to show right now is hard optimization problems. And we have seen that we have performance advantages on solving these problems, and the most important one is energy. So just one sec. Yeah. So I will show you like a little brief on the relevance of this application. Where are we working on that? Then a little bit on the architecture itself, that this is a research chip that we have been developing, and we have like the chip and the systems for it. And then the full stack software that we have been developing to allow both prototyping and application development. And then how this full hardware and software stack has shown that graph algorithms are actually quite suited for what we call neuromorphic computing. That is like this hardware that is post-von Neumann and focuses on trying to mimic certain properties of the brain computations. And then on top of this framework, we have done the lab optimization, which is a library that's precisely for this type of problems that show advantages. And then I will show you a little bit of how does that work under the hood, and then how does that result in improved efficiency. And just a little pitch on the Intel neuromorphic research community that we have, that you all can join and then get access to the technology. So first, like constraint optimization problems refer to optimizing some quantity that is of interest in any system that you have, subject to certain restrictions on the values. And that very broad and abstract definition actually applies to a lot of important applications, especially in industry, but also in academic, right? So you have from finance, communication, robotics, everything. And I will just outline 2 examples that we have explored with our solvers. So for example, in the field of robotics, you have sometimes the problem of trajectory optimization. Being it that you have like an arm robot and you want to optimize the movement of the end actuator to move some objects, or that you have many robots, like here we are seeing fleet management, for example. We have many robots that or autonomous vehicles in the picture, that you need to route them from some source to some destination. And you want to minimize a quantity, which is like the travel distance or the time you spend to go from one point to the other, or a product of the 2. And you want to satisfy the constraints that you don't have collisions, right? And that you follow, for example, the traffic rules in this case. So this is an example of constraint optimization problem that we are actually having some examples on that. And other example is in logistics, all this area that tackles scheduling, package delivery, routing of vans through the world, delivering goods and services. So there, you want to assign the largest number. For example, when you do logistics for example, the German rail network, which is another example that I will show results on, you want to optimize the number of assignments from source to destination that you have as requirements, given the trains and rails and timing constraints, the capacity constraints as well that you have. So these are 2 examples, but then you will see, like, because of the very broad definition of constraint optimization, you can also find like many applications that are where these problems are important. But many of these problems are actually NP-hard if you're familiar with the nomenclature, which means that the time to solution explodes exponentially with the number of variables that you have. So these problems remained very hard to solve despite being very broadly applicable. So for that, we are exploring the technology, as I mentioned, is brain-inspired, And just as motivation, if you compare like a top technology like the drones that became very viable recently, and they are becoming very fast, and you can have some very fast drones competitions versus cockatiel parrot, right? And we look at biology, and the power that the drone consumes is quite many orders of magnitude larger than the parrot. The parrot is at 50 milliwatts. The drone needs 18,000 milliwatts, and we are talking here about computing, right? The weight is also much larger than the brain. And you need to have all these databases to train some networks in the drone to be able to control at a walking speed to go through gates without colliding. Just is impressive technology, but compared to a parrot, that navigates at 35 kilometers per hour, that's like a very fast bicycle, without colliding with anything, and actually at the same time making some problem solving, researching for food or things like that. And it can learn to speak English. It can learn to manipulate cups for drinking. And you see that the mass and energy requirements from the parrot are very low compared to our toughest technology. So that means that there's something in the brain that we have still not really cracked about how computation works. And if you were to zoom in the brain of this little parrot, you will see a lot of neurons, which I am depicting here as this body here. This is a neuron, which is just a specialized type of cell in the brain, and actually in the body you may have many of them. But the important characteristic is that all these neurons, they connect, every neuron connects to about 10,000 other neurons, right? And they do some computational process through biology on the body and integrate all this input that comes from other neurons and decide whether to send these messages through the synapses. You have these branches that are called axonal outputs, and they connect to dendrites on other neurons. And what you have is like chemical electric pulses going from one neuron to the other, but every neuron connects to about 10,000 other neurons. And these other neurons can connect back to these ones or to new ones. So you end up with a very complex neural network that has recurrence, that has temporal dynamics, that shares these messages through the synapses with some other computational properties there. And you can actually model these neurons as dynamical systems. So yeah, the actual biological model is super complex, but you can approximate it with some discrete update equations that integrate some input and decide on some output. And is this very complex dynamical system, which gives this emergent behavior of intelligence, of problem solving, of a very high efficiency. So our value proposition here is to come with some hardware that tries to implement these event-driven and discrete dynamical systems dynamics, like a sparse updating and asynchronous communication. We wanted to put it in a hardware chip that then we can build systems with them and then have the full software stack. I will go in this element a little bit more in detail in the next slides or in the QA question if there's one. But the thing is, we're building the hardware, the software, and the community around this to really explore how we can really harness these brain capabilities. Of course, we are not the first ones doing it, either in industry or academy. So there are groups like Spinnaker in Manchester, which we had actually somebody from there talking earlier. And then we have like industries like IBM also having their technology. But I will argue that Loihi, in some respect, is the state of the art in neuromorphic computing. So the difference between neuromorphic computing and parallel computing, that's probably one of the most used by the people in this conference, is in parallel computing, you have this vectorized input-output that has a lot of processing of instructions in the middle, right? So you have massive data coming in, massive computation going out in the middle, and then you get a massive output on the end, right? In neuromorphic computing, we don't have this separation between memory, fetch, compute. We have memory and compute integrated, like a neuron in the brain. We do it a fine-grained parallelism with memory and compute happening in the same regions of the chips. And we also have, instead of having like these full vectors of input-output, of course, we can have input and output to our neurons, but our networks are actually dynamical systems that they have a state. So the functions here that are being evaluated, they don't have a state. The state is the input. But in our networks, the full network has a state in itself that can be influenced by inputs, either from sensors, cameras, receptive fields, audio signals, whatever. The network evolves through a lot of recurring connections, dynamics in every one of the nodes, and messages going through the edges, and it produces some output, or the output can be the full state of the network as well. So this is a very different paradigm from conventional parallel computing, which also allows you to do these batches of data that you want to process one at a time. Whilst here you are processing everything asynchronous on demand, right? Not at the same time, but on demand. And then these nodes that we have in the neurocores that we call, that are the cores of our chips, and that implement these dynamical systems, they allow you to implement many types of dynamics, right? So this is probably too detailed, but here on the top left, maybe I should put a pointer. So this is one of the simplest neuron models that include temporal dynamics, right? So all these little vertical lines here are signals coming from other neurons. They are being integrated. You have some update equations on the node, and then you send some output. This becomes discrete dynamical equations that you map into some instructions in some patch, in some assembly language style of coding, and then you are able to execute these instructions on the neurons. And this is different from artificial neurons, although artificial neurons, you could implement them, but you are forcing synchronization. But the main difference between the artificial neurons and deep neural networks of deep learning is that they are stateless, whilst our neurons, they actually have a state that you want to evolve. And you can go to very different dynamics here. Like I'm just giving an example of resonant on fire, adaptation, sigma delta encoding. Well, so some technical names for these dynamics that when you get an input represented by this spark, then the system evolves and the state of the system evolves in a particular way. And this is just a little detail of what you have as tools to put them in a neural network of millions of neurons or thousands of neurons and connected in different ways to manifest computation of the more macroscopic level. I will show you a little bit more of detail of how these neural networks result in computation at the larger scale. So Loic itself, this chip, is made of all these neurocores here, which are very small and simple fixed point architecture. That's an important caveat. We don't have floating point there. Which are specialized arrays of memory that allow you to implement that neural models. And then we have some more conventional computing cores here, right? CPUs. And then we have input and output to either other chips, because we can scale this architecture to multi-chip as large as the design allows, to 100 billion neurons, for example, just to give an idea. And then we have an interconnect for sending all these messages among all these different neurocores. And then the different input ports allow you to also have different interfacing for different sensors and different computing. So with a throughput of 10 gigabytes of Ethernet input that you can put there. So we have compute and memory integrated. We have temporal neural models. We have event-based communication. Ideally, sparse connectivity, so that results in sparse dynamics as well. And you only do computation when you need it. So if you see like the parallel computing, you are updating all these units at the same time, even though sometimes you have zeros. Of course, you have sparse codings for that. But we want to only do computation when it's needed. So there's like this sparse connectivity and sparse dynamics that arises on the chips. Then first we had a Loic 1 chip that we released to the public, and now we are in the Loic 2 version, which is 10x faster, 60x more bandwidth, and it allows up to 1 million of neurons in a single chip, right? You can put on these chips that are brain-inspired, and that will be able to implement either deep learning, vector symbolic architectures, constraint satisfaction problem solution. You can put them in different boards. Like here, I'm showing a couple of point board that is made of 8 chips, and they are stacked top and down. That's what you only see 4. And we have, from the first generation of the chip, we have other larger boards with 32 chips per board. But we can build either stacks of these couple of point boards for things like robotics, drone technologies, or we can have this more data center style of racks. We have a Kapoho point, and we can put a Kapoho point. This is Pohoic Spring, sorry. We can put Kapoho point in a full system that allows you interfacing with sensors, with actuators, in, for example, a drone or a robot, a quadrupedal robot or something like that. And once you have this hardware, then you need a software to actually use it, right? So our software framework, after many iterations and learning, is called Lava. So Loihi, the name that you saw here in the chip, is a volcano in Hawaii, right? That is emerging from the surface of the, from below the surface of the ocean. And the analogy is this is an innovative technology that we hope it comes out. It is an emerging technology that hopefully erupts. So our software framework is called Lava, which is a framework that allows you to use these systems that I showed you based on Loihi, but also GPUs, also maybe FPGAs. So you have all these heterogeneous computing platforms, maybe with also sensors and actuators, and then you wanna coordinate all of these in a single computing system, right? So there are not systems that are both allowing you to this heterogeneous synchronization, like for example, ROS exists for robotics, but is not bespoken for neuromorphics. So we were trying to fulfill that extra need of allowing neuromorphic prototyping and development of algorithms on top of being able to allow all this message passing coordination between different hardware backends. And that involves creating the full runtime, the compiler, and a library of the elements of that we use. So in short, Lava separates interface and behavior. So we offer some processes, which are the interfaces, and some behaviors, which we call process models. And then you can create many instances of that and connect them. So if I want to do a neural network, I will have processes for neurons, processes for synapses, replicate them many times, and then connect them through the ports that they have. And the process models, it's not the interfaces, they will describe the dynamics of these different components. And once you have that, you will have a standard library of processes that you can use, but you can also develop your own ones. And then you start to develop libraries. So the one that I am going through in this talk is optimization, but we have also some neural attractors. So imagine attractor dynamics created through neural networks. That's a library for that. And then we have a library for deep learning. So translating networks that have been trained maybe in GPUs or something. And then you want to translate it and run it in our neuromorphic architecture. There's a library for that. And we hope to grow these libraries, everything with the community. So we are like putting the seed there, and the community should like dictate how this evolves. Same is true for the internals of every library, what are the algorithms and the applications that are more relevant there. And we also try to offer some utilities, like for example, when you're exploring this new technology, you want to understand what's the efficiency. You want to understand how the things are moving inside and outside. So we have utilities like a profiler, visualization, conversion from flow to fixed point architecture. Some of these things are in development, the other ones are ready. But once you have all these software stack, you can integrate other frameworks. Probably you know TensorFlow for deep learning, ROS for robotics. Nengo is a little bit more on the more biologically inspired way of creating intelligence processor. But then this software framework controls the hardware that I just exposed you to, right? And it's open source, it's out there. You can visit it in GitHub and contribute and make pull requests. You're more than invited to do that. So the project tries to also support some public forums, have all these applications and algorithms that I show, but also give access to, you need to do some subscription because the hardware platform, of course, is a private IP, but you can also get execution on the actual hardware, right? And we're trying to provide benchmarks, as the one that I will show next, to show the advantages of this. So I will close over this a little bit. This is just about the libraries that I mentioned that Lava includes. And these are new libraries that we are thinking that we could develop, like Lava Robotics, Lava Evolve for evolutionary algorithms, Lava UI to offer graphical interfaces, etc. So with all this infrastructure, we did with the community research on what type of algorithms and applications could be really suited for this, right? So you will think like maybe things from neuroscience. Maybe if you have a map of the thalamocortical circuit for understanding sleep behaviors, you may develop something that is interesting for medicine. Or maybe you have some motives that allows you to create networks that will control robots. Or maybe you have something that is pure mathematics and exploration of geometrical spaces, I don't know. So you have all these options to make computation with this new paradigm of architecture. So we did some exploratory research around that with the community. So some parts were done by us, others by the community, and we condensated all the results in this plot that I am showing. So what you see here is like a plot of, here is time to solution on the left, on the vertical axis. On the x-axis, you have energy ratio. So you have the ratio of low-E versus some architecture, being CPU, GPU, Movidius, True North, another hopefully state-of-the-art architecture that we are comparing low-E against, both in energy and solution. And this line here, dashed line, it implies that low-E and the other architecture are on pair. So they perform equally on these two metrics. If things are here below, that means that these applications are worse on low-E. If they are here in the top, they are better on low-E. And then what we found is like feed-forward deep neural networks for low-E one at least, and without batching, because the architecture is not the same for batching, they don't really perform better. You have some advantages here, which I mean, they are interesting because we are talking about many X advantage, but we are looking for orders of magnitude advantage, right? So sometimes low-E is even worse. But then if you look at these networks here on top, which use recurrence, so connection to other system and from the system back, so feedback loops, and that they are sparse and graph-based. So all these networks actually show a lot of advantage. So you're seeing here like 1,000 times improvement in speed to solution, right? 100,000 times better energy. So here is where the energy efficient towards sustainability of the conference comes in the mind. When I was thinking what to present, this is what I want to insist on. So we are finding here that certain applications have an energy advantage. So you have a workload that you will solve in a state-of-the-art architecture, and then you can go many orders of magnitude more efficient, less energy required to solve the same problem, maybe faster. But then all this energy efficient means a lot of energy savings and hopefully a more sustainable computing platform, right? So here in these ones, we have things like, controllers for robotics, we have graph search, we have constraint satisfaction, we have search in like a first neighboring search in high dimensional spaces, and sparse coding. All these problems are recurrent. The networks that result to solve these problems, they are recurrent, so full of feedback loops, and they are also graph and sparse. So with that, I'm probably running a little bit short on time. So what we wanted to do is like to implement these problems here, we had to do a lot of hardware engineering and science. So we want to simplify that process. So with Lava and then Lava optimization, which I will not go in deep, I am just showing like the vision for Lava optimization, is that you have a problem with some functional behavior, performance measurements, state variables, whatever. You as a user convert it in an optimization problem. So you will end up with some objective function, whether you want to maximize, minimize. You will have your variables with the respective domains and some restrictions or constraints on that. And ideally, we offer this boundary, this interface here, where you can give that problem to our stack, and our software stack will try to convert whatever you gave here to a network topology, to a particular event-driven network dynamics, so a dynamical system that solves the problem when you put it in a network, to different state variables, to the different types of messages, and then all the way to compile it to the architecture. So we want to make this process of the hardcore engineering less exposed to the user, and the user comes all the way to just give an optimization problem. Of course, we cannot tackle all of them given the fixed point architecture. Of course, as you have advantages with the different architecture, you also have limitations. But then this log optimization library, we are focusing on a subset of the possible constraint optimization problems. So optimization, you have a function f. You want to, let's say, minimize it. If you want to maximize it, use invert the sign. And you have that function, you want to minimize it subject to these are some vectorial functions giving you constraints on the values of that domains that you have X, or on the mutual values that they have. So a constraint optimization problem is just that. But then if you start to look at the shape of F, the shape of G, or the relations, you will end up with different problems. So you have here, for example, the classical integer linear programming or even linear programming, this one here. So F is linear, the constraints are linear, the variables are allowed to be continuous. So this is the typical linear programming problem that is, for example, very used in finances, right? If you then allow the variables to be some are integer, some are real, you have a mixed problem, which is way harder than the case of continuous problems. And you can make the cost function quadratic, you can make the constraints nonlinear as well. So you have all these type of problems, and we have demonstrated a constraint satisfaction version of integer linear programming, quadratic programming, and QBO, quadratic unconstrained binary optimization, which is very used in quantum computing. These 4 types, we have demonstrated solution to them in low-E. And the other ones are under research right now, especially the mixed ones that have a lot of interesting applications in robotics. The important thing here is like the continuous problems result in convex spaces. So these are contour lines of a 3D shape. Well, it can be more than 3D. And these shaded lines are planes. So the thing with convex problems like QP or LP is that they are solved through gradient descent. Or gradient descent usually works pretty well. When you have integer or binary variables, your space becomes combinatorial. You need suddenly to look at all the possible combinations of values. So as you see here in the bottom. And that search becomes way harder because there's not like a systematic gradient descent that will take you all the way to the global minimum. You will get them stuck in local minimum. That's what makes that problems way harder because for once, some algorithms like gradient descent don't work for the global optimum, and also the number of combinations grows exponentially. So the neural networks that we have, so the network is here on the right and the dynamics is here on the left. You start from some random initial state, then the dynamics evolves your network down the hill, for example. But we also allow some stochasticity on the networks or some attractor dynamics, things like that, that take you to the minimum. Here, for example, you're getting stuck in a local minimum, but you went down the hill. But you also have these other dynamics that tries to push you out of the local minima and take you all the way to the minimization of the quantities you are interested in. So you go to the full solution of your problem through what you saw here in the right, all these messages going between dynamical systems in a network. So yeah, these are some animations on how this works, but given that I have a minute, I will go directly to the results. When we benchmark this type of solvers on the low-E architecture, we see, I will show you 4 examples, constraint satisfaction problems, quadratic programming, here QBO, and then integer linear programming. And the red line is this in the reference architecture with a reference software, state of the art, hopefully. And the blue one is low-E architecture with our software research and application. And you see consistently that in these problems, you have 10 to the 5, 10 to the 10, 10 to the 3, or 10 to the 5 again, orders of magnitude advantage in the product between latency and energy, so energy delay product. So you're saying that there's like a huge gap of, this is 10 to the 5 increase in energy delay product, right? And that's consistent across many problems in all these taxonomy of problems that I showed you. I wanted to go in detail in one of the examples here of how that happens, for example, for QBO, but probably I think that that's enough for now. Just to wrap it up, Like at the energy level, you see here, for example, 3 orders of magnitude increase in efficiency when you are looking at a problem being scaled up from left to top for a problem that has a NP hard complexity, which is Cubo, or in the particular example, is the maximum independence set. So that's what I wanted to transfer, that this technology that we have developed, it allows a much more efficient way of solving hard constraint optimization problems. And you're more than welcome to join our INRC community to get access to the hardware, to get access to the trainings, workshops, the community, to make questions, maybe publish papers with us, or we can join with our support. And yeah, this is a community of 180 plus members from industry and academy, that we are all working together to make this neuromorphic technology a reality that goes after the research state into commercialization. And typical benchmark disclaimer information about reproducibility of results. So thank you very much. I hope that was instructive in any way. I cannot hear, but given the movement, I guess you can hear me.
Okay. Okay, there's always a little delay. Yeah. Okay. So thank you very much, Gabriel, again for a fascinating talk. I'm sure there will be some takers for your offer to join your community. Yeah.